Okay, maybe I. So let me just recall very few facts from yesterday's talk. So maybe you should remember that we quantized a few classical Markov chain-based walks, and one of them was the quantization of what I call the lazy walk, and this gave rise, among others, to an algorithm which has the following parameters. So the cost, this abstract cost I am using in the analysis of the algorithms is the setup cost. So it's constructing the one eigenstate of the walk. Then the update cost is the cost is one step of the walk, and the checking cost is to check if an element in the walk, a vertex in the base set is marked or not. And then what we could, among others, do is an algorithm where at the cost of one setup and 1 over square root of epsilon, where epsilon is the probability of a marked element in the stationary distribution, times 1 over square root of delta, where delta is the eigenvalue gap of the original Markov chain. So that many update operation and 1 over square root of epsilon checking operation, we can find marked elements. So this is the analog of the lazy walk, where there are no square roots classically. And this is just a very simple algorithm that you kind of try in the uniform in the stationary distribution, and if you don't succeed, then you make enough step to mix again the walk and then try again. Okay, now I gave a few examples in the simplest model of the query computing. I analyzed Unrich's algorithm about element distinctness, and we could show that on the Johnson graph in m to the 2/3 operation you can decide if there is a collision. Then I spoke about k-collision, a little bit about matrix verification. I explained the quantum Markov puzzle, and I stopped here. And I just very shortly mentioned one more example, and then more in detail a second one. So this is group commutativity. So basically you have a big group, and think about that there are n generators, and your access is again query access. You can ask what is I times j, then you get it for $1. And the question is this commutative? So obviously classically, at least deterministically, you have to make n square queries, and this is a kind of fun algorithm of Igor Pak. It's again classically, if you randomize, you can spare, you can get down to n to the 4/3, and it turns out that the quantum algorithm of Magnias and Nayak does it with basically the square root of this classical randomized complexity n to the 2/3. So I don't go into the details of this algorithm, but Steve asked yesterday if I know any algorithm which doesn't work on the Johnson graph. Now, stricto sensu, this is not working on the Johnson graph, but on some graph which is closely related to the Johnson graph. So here I am not picking up R element subset of the base set, but sequences of different elements, and the walk is a little bit different, but to be honest, at the end of the day, it's similar. Anyway, it's a very nice thing. If, for example, you want to teach randomized algorithms, even classically, you should check this paper. I guess it was never published. You can find it on here. Okay, so that's group commutativity. And now I go much more into details about triangle, because triangle is kind of the paradigmatic problem for this quantum walk and learning graph-based query algorithms. And so let me tell you what is the state of the art, not right now, but somewhat later. So the problem is the following. I have a n square or n choose 2 variate function, and you think about this n choose 2 variable as the edge slots of a n vertex graph, undirected graph. And one query is that is this edge there or not? So that's what costs you $1. And the problem you have to decide that is there a triangle there? And classically, it's quite simple to show that you really have to ask every query. So until the last moment, deterministically, you don't know. And there is a famous conjecture which actually says that for these type of problems, where these type of problems technically are monotone graph properties, even randomized algorithm have to ask basically every question. So n square question, order of n square questions. What can we do quantumly? So the trivial thing is that we can play Grover on the, so a triangle is determined by 3 vertices. So
because it's not a conjecture that this is n squared.
You mean the randomized? I am sure you can prove it. Yeah, it's not a conjecture. No, for this problem, it's not a conjecture. No. So yeah, so the classical complexity even randomized is order of n square. And so the trivial Grover things would be to try all three tuples as potential candidates for the triangle. So this is n's cube possibilities, square root of this is n to the 1.5. So that's what you can do trivially. So this first algorithm, it's now almost 9 years old, is an algorithm which solves it with n to the 13 over 10 queries. It's kind of a weird number, but that's what came out. And so I go a little bit into detail here. So the algorithm is again on the Johnson graph. So you remember I have n is the number of vertices, and I am looking all subsets of the base sets of size r, where r is again a parameter. And I will say that an element, so this is again a huge graph, yeah, exponential size graph, if r is something like n to the some power of n. And I will say that the vertex of this Johnson graph is marked if it contains a triangle edge, that is, contains two vertices such that they are connected, and part of the, imagine that there is a single triangle to be simple. And then if a subset R of size little r contains the two vertices which correspond to the triangle edge, then it is marked. So that's the definition. Okay, so what are the parameters of this log? So what is the chance that I have that a vertex is marked? Well, so I pick A and B, and then both A and B should be there, and then I am picking up R element out of n, so this is R over n, basically independent almost, R over n squared. So this is the success probability. As we said already, the eigenvalue of the Johnson graph is 1 over R. Another data structure which I am defining is a little bit more interesting than yesterday. So the data for this vertex of the Johnson graphs will be the restriction of my input graph on this R vertices. So again, R is some subset of the vertices, and the data with respect to this R is just the graph, the restriction of the graph, the induced graph by this subset R. Okay? Now what are the costs? So the cost of the setup cost is, well, if you have a subset R of the vertices, the graph span is you have to ask all possible edges, they are R square of them, so the setup cost is R square. Now if you make an update, then it means that you kick out an element for your set and you bring in a new, then you have to know that this new element is related or not to the others. So there are R possibilities, this is basically R, 2R. And my claim is, which is the interesting part of this algorithm, that the checking cost can be done with that many operations, and I will prove this on the next slide. But believe it for a second that the checking cost can be done with square root of n times r to the 2/3. So then the complexity, I just plug in the parameters. This is the setup cost, this is the 1 over epsilon square, and this is, let's write it up. And then if you optimize here r, it turns out that r turns out to be n to the 3/5, which is kind of funny because you have 3 terms, and this is not. You see, this is less than n to the, n to the 12, 10 r square here. This is less than what I'm claiming, but the other 2 turns out to be n to the 13 over 10, so that's what I claim. So let me go to the checking cost. So why the checking can be done in square root of n times r to the 2/3. So again, what is my problem? So I have a graph. This is the restriction of the original graph to this set R, which I know. So that's the data structure gives me. So there where I'm using that, carrying the data. This helps me now. And then I have to decide that, is there a triangle edge here or not? So is there here an edge such that, like this green edge, such that, let's say that I have a green triangle and this is one of the green edges. And so basically, to have a triangle with some edge here means that you have to find the third vertex, V, and then V and this edge inside the graph restricted to R has to make up the triangle. So for the third vertex, I'm just making a blatant Grover search. This gives me the square root of n. So again, that's what I'm claiming. And now let's imagine that I have a fixed vertex, and my task is to determine that is there a triangle such that V is a vertex, now is fixed, and the other edge of the, and so V is related to 2 vertices inside this graph such that these 2 vertices are connected by an edge. So obviously, if I find an edge here such that for both endpoints of this edge, V is connected by an edge, then I have a triangle, and that's if and only if. Okay? And this, it turns out to be, it's again a kind of unbinding problem. It's a kind of element distinctness, because I can say that two vertex are here collision if and only if they are related by. So I'm defining a function, a new function, an oracle function over the vertices of this restricted graph. And basically, I will say that two vertex are in collision if and only if they both evaluate to 1, meaning that there is an edge between V and this vertex, so this is the meaning of 1, and they are related. And I am really just asking that are there two 1s there? So again, the definition is that a vertex here is 1 if and only if it's related to V. So this I can get with one query, and I am asking for two 1 vertices such that they are also having an edge between them. And as I mentioned yesterday, in this element distinctness problem, really, it doesn't matter that what is a relation I am deciding. So yesterday I just wanted to have two elements which are having the same value. I now want two elements which have the same value, 1, 1, and also are related by an edge. But this being related by an edge doesn't cost me anything. So I can just solve this problem exactly with the same routine as yesterday, meaning that the cost of this problem is, well, I am on a set of size little r to the 2/3. So that's why square root of n coming for the search of this V, and then I am just plugging in, if you want, inside the checking procedure there is another element distinctness problem, so an element distinctness inside a second element distinctness, and that's how I am getting the checking cost, which is this r to the 2/3 here, and this is the clover. Okay.
Because are there some errors that you have to keep
Yeah,
somehow?
that's correct. I am. Yeah. Almost everywhere, which I am totally neglecting. Yeah. Okay. Now, so that I will come back to this triangle because this is not the last word. But now let me go to the main part of today, which is basically learning graphs. And for this, I have to speak a little bit about quantum query complexity. So this is a vast subject, and I am just touching at some level the whole thing. But let me say just brutally that today we have a really quite good understanding of the quantum query complexity. So among others, we have a perfect characterization and a very operative characterization of the query complexity by semi-definite programs. So you have seen hundreds of semi-definite programs this week, so I don't say anything more about them globally. But just let me tell you that here is one way, if you want, even you can define query complexity, but certainly equivalent characterization of quantum query complexity. So let f be a function which goes from any, I don't have to be binary, so let's see, it's a B-array alphabet, and I don't even have to be a complete function. So it can be a promise problem, so capital D is just a subset of little d to the n, so it's an n-variate function, say, but Boolean, so the results are 0 or 1. And the quantum query complexity, so how many queries you have to ask to compute f, can be characterized by the following semi-definite program. So, okay, it's let me say this way: you have to come up. I describe this as a vector program, which is equivalent to the matrix characterization, semi-definite matrix characterization. So you have to come up with a bunch of vectors. So basically, for every input, x, potential input, you have to come up with n vectors. And the ith vector, say, for x is denoted by uxi. Okay? And then the function you want to optimize is the following. For every x, you look at these n vectors which correspond to x, and you sum up the norm squares. For every x, I am having this sum, which is just the n vectors corresponding to x, the length, the sum of the lengths, to length square, and I maximize over x. Okay, so that's the function I want to maximize. And what is the subject? So the subject, the constraint I have is a little bit weird, is the following: for every two inputs which have different values, so x and y, such that f of x is different from x of y, I want the following. I kind of make up this scalar product, kind of scalar product. So I am taking the sum for all i's such that the ith bit of x and y are different. Has to be some I because f of x is different from f of y. And then the corresponding scalar, sum of the corresponding scalar product, sum over all these i's, has to be 1. So this is a, okay, so that's the semi-definite program. And so this is a kind of tough program. So the constraint is really tough because it's a kind of very precise constraint over a weird summation. You know, you have to be really 1, not plus or minus 1. And it's really, if you want to, you know, construct such a vector system, it's not so easy to come up with a bunch of vectors which satisfy this condition. And so that's why somehow, you know, we didn't get. So this theorem goes back. Basically, there is the so-called generalized adversary bound, which is basically stating the dual of this lower bound, and as it turned out after a few years that it was actually not only lower bound but the exact bound, and characterizes the complexity. But we didn't have, you know, hundreds of algorithms which just construct these vectors because it's not easy. And basically the learning graph is a very nice way to construct a specific solution to some restricted version of this vector program. So that's the basic idea of Belov that gives you a relatively simple way to construct this. Okay, so before defining it, let me just observe that.
Miklos, is
yeah.
For the exact query complexity
Yeah.
or the bounded error?
No, bounded error. Sorry, bounded error. Now, so let me just observe that instead of this objective function, I could also you know, kind of separate the positive and negative inputs, and then, you know, doing this. Oh, I didn't say that. Of course, what you want to do that once you have your vector system, then you get this quantity, and then you take the best vector system, so you minimize over all possible vectors. But so this optimum could be also just rewritten as the, you know, the geometric mean of the same thing, but you know, here you take just negative inputs, and here you take just positive inputs. And the reason is that you know, in this scalar product, if you multiply positive vectors by 10 and divide negative vectors by 10, then the scalar product is still the same, obviously. So therefore, you can suppose that this maximum is obtained simultaneously on positive and negative inputs. Will come later. Helpful. Okay. So now, again, learning graph is a very specific way of creating such a vector program. So what is a learning graph? So the learning graph for, again, the n-variate function on alphabet size d is a rooted, weighted, directed acyclic. Okay, maybe it's too terrible to read. So here is a learning graph. So what I am having, so basically it's a subgraph of the hypercube. It's a directed subgraph of the hypercube. Okay, it can be weighted. So here, for example, and the way I represent the hypercube, think about the vertices of the hypercube as subsets of the first n integers. And every subset corresponds to some indices, and basically a vertex with some subset of indices tells you that that's what you learned already. So these variables were already learned. So you kind of start in the empty set where you don't know anything. And then every edge goes from a set S to another set, which is just having one more element. Okay, so maybe I come back here. So every vertex is some subset of the n indices. Root is the empty set. Every edge goes from some subset S to S union I for some I. Okay. Now I have to specify for every edge a weight. So that's simple. For example, in this example, the weight is just 1. This is the black one. And then the really interesting part of the definition is the following. Whenever you have a positive input, so y such that f of y is 1, then you have to specify a unit flow. So the unit flow starts, you inject the unit flow at the empty set, at the beginning of the graph. And what is important that you have to take out this flow, that is the sink of the flow, has to be sets such that the y if you restrict it to just the variables inside the set S, these sets already constitute the one certificate, which means that it's enough you know y on the variables which correspond to the subset S. If you know this part of y, you already know that the value of the function has to be 1. Okay, maybe let me show you here the learning graph for the OR function. So here the point is that if you have a positive input, so the OR of n bits, x1 or x2 or xn, if it's a positive input, which means that necessarily there is a y such that xi is 1. So then, for example, I can take the flow simply, which goes from the empty set to the singleton I, xi is 1, and put the whole flow. It's a trivial flow, just the whole flow is going from here to there. Okay? But the point is again that once you know that xi is 1, you don't care about the other variables. Your input already tells you that this restriction of the input, that the value of the function is 1. Okay? And sometimes, it will be helpful for me later that I can take edges, but this is just a technicality when I am going from a subset to a much bigger subset than just one more element. And in this case, I say that if I add 10 elements, that the length of this edge is 10. That's just a technicality. Okay, now what is this clear? Well, if you don't say that, no. Yep. I will give more examples immediately. So what is the complexity? So I define the negative complexity and the positive complexity of the learning graph, and the complexity is the geometric mean. Okay? So what is the negative complexity? The negative complexity is just the sum of the weights. If I have lengths, then I weight with the lengths, but forget about it. It's just sum of the weight. So again, important, the graph itself is an object which doesn't depend at all on any input. So the graph is, the weights are given once for all, and the sum is given once for all, input independent. That's the negative complexity. Now for the positive complexity, I am interested in the positive inputs. And for every positive input, again, forget about this. Basically, I am looking at, you are mostly physicists, at the energy of the flow. So I am looking at the sum over all edges, the flow on this edge square over the weight. Okay? And I am maximizing over all positive inputs. And that's the positive complexity. And the complexity of the learning graph is the geometric mean, and the complexity of the learning graph complexity of the function is you take the best possible learning graph which computes this function, and then the complexity of this learning graph. So how about the OR function? So, okay. So what is the negative complexity? I just have, so again, my color coding will be that the black things are always just the weights, and the green will correspond to the flow. Always. Okay? So green is the flow, black is the weight. So the weights, total weight is just I have n edges, each of weight 1. This is n. So how about the energy of this flow? Well, it's a trivial thing. It's just 1. The geometric mean of the 2 is square root of n, which gives that the learning graph complexity of the OR function is square root of n. Okay? Now the basic theorem which shows that this is indeed a relaxation of the quantum query complexity of this vector system. That is, the quantum query complexity is certainly less than the learning graph complexity, because I just relaxed my optimization problem is coming from Yelov, and the proof is actually quite simple. So let's suppose that you have a learning graph. So how can I create my vectors? And so the way to create the vectors is the following. So let me divide the edges of the learning graph into n buckets. So the ith bucket is just those edges where I adding to some subset S the ith index. So the edge is S, which doesn't contain I, and then the other edge of the endpoint of the edge is S union I. Okay? And then I am defining the vectors corresponding for, say, a negative inputs. As I am summing over, I have to define for all I, the ith vector corresponding to x, and for an I fixed, I am just summing over all edges in this subset, in this set of edges E sub I. And So I am, let me put it this way, two registers. In the first registers, I put the beginning of the edge, and in the second register, I am putting the restriction of x to this subset. And the amplitude, so to say, is square root of the weight. And for positive inputs, it's the same, except that the amplitude will be the flow over square root of the weight. And it's really not that hard to see. Maybe I don't go into details, but you can just compute that. First of all, the optinoids program is exactly what it has to be. And the important thing is that y is the constraint satisfied. So it turns out that if you make up this sum, which is supposed to be 1, then it's exactly a flow through a cut in the learning graph, and the cut is determined by I have my x and y, so these two inputs which are having different values, and I look at all indices where they are identical. And then my cut is defined that left hand side I have all subsets which are contained in this set where x and y are identical, and the right hand side is where there is at least some index where they are different. So obviously the empty set is on the left hand side, obviously sinks are on the right hand side, since f of x is 0, f of y is 1, so has to be some I where they differ. And it's really not that hard to see that the summation is exactly the sum of all the edges which go through this cut. And if you have a unit flow, then its value through any cut is also 1. And that's why the constraint is satisfied. So that's a nice thing about Belov. Gives you a completely combinatorial way of satisfying this constraint, because the unit flow through every cut will be always 1, and therefore this constraint, which turns out to be the flow through some cut, is obviously again 1. Okay. Now, so what I will try to do is I kind of go again element distinctness, because then you will see really how this learning graph works. I mean, the OR function is too trivial to really understand, and of course now you already know a little bit element distinctness, because yesterday we have seen the quantum work, and then I really do the computations, and once you have seen it, you will maybe believe me that all the more complicated things will be somewhat similar computations, but at least you have seen the principle. So for this, let me just simplify a few things. But where I am heading for is really, at the end of the day, to give you some extremely simple combinatorial principles which make a learning graph work. And it's really somehow kind of funny that this quantum query complexity, end of the day, it comes down to some very elementary properties of classical combinatorial properties of graphs. Much simpler than eigenvalues and stationary distributions. Really just degrees and the number of vertices, things like that. Okay. So for that, let me just call the level of in a graph is just a bunch of vertices which have the same cardinality. So you can think about that this is a single empty set. These are singletons, sets of size 2, and more generally can make this big step that, for example, these are all sets of size 10. And then here, really, every edge corresponds to adding 10 elements. This is just a kind of abbreviation of 10 long normal steps. Okay? Now, the point is that if I structure the learning graph this way, then if I only have a constant number of stages, then I can compute the complexity stage by stage. And the definition of the complexity is exactly the same, positive, negative, geometric mean. And then I do it for this stage, and this stage, and this stage, sum them up, and if I had only 3 stages or some constant, then that's okay. So otherwise, some Cauchy-Schwarz comes in, but for a constant number of stages, it's not cheating. Okay? And so here is this point where I'm coming down to the starting this very simple characterization of the complexity. What is the complexity of a stage? So basically, imagine that I am in a very, very simple situation where, so here I have this is the set of all vertices V, so I have cardinality of D vertices, and some set W got the flow. So again, green is the flow. And imagine that the flow is uniform, so every element of W got the same amount of flow. I'm really simplifying everything, but it still remains basically true for the general case. And imagine that, that the graph is such that in general, you know, for the weights, I have d vertices, so the degree of every vertex is d plus, say for the out degree. And out of this d, if the vertex gets some flow, they are g plus again, that the flow goes out. And this is uniformly. So for every vertex in W which gets some flow, sends it to g plus vertices. So then what is the complexity? And you know, it's completely trivial, plug in the formula, it will comes out that, again, think about that the length is just 1. So this, if the length is 10, then it has to be always multiplied by the length. But the point is that the complexity, so this geometric mean comes on to what's called the vertex ratio and the degree ratio. So the vertex ratio is just the ratio of the total vertices over the vertices which got flow, and the degree ratio is the ratio over the, you know, the generic degree of a vertex over the number of the degree, the number of vertices where the flow is sent. So that's a very simple, totally combinatorial thing, the vertex, the geometric mean of the vertex ratio and the out degree ratio. So that's the complexity of the stage, and just sum it up. So let's see what does it give for element distinctness. I recall I have this function goes from n to n, and I am looking for two indices such that the ith element is the same as the jth element. Okay. So the eighth element is the same as the bth element actually. And so you know the first thing you could do is mimic the OR function. Let's see what does it give. So that's what I call, as you see in a second, by the bad learning graph. Yeah, but I could do, you know, in OR function I just loaded, you know, the one step the index, which was interesting here, I can do in 2 steps. So more precisely, I start with the empty set, then here I put all possible singletons, here I put all possible 2 tuples or 2 element subsets, and every weight is 1, and if I have a positive instance, so say A and B are the collisions, then the flow is just going from the empty set first to A and then here B, and you know, don't tell me that, yeah, here. I don't care about constant 2 before Harry asks. Okay, so what is the complexity? Well, it looks like complicated, but really. So let's see the degree and the vertex ratios. Yeah. So what is here the degree ratio? It's, you know, 1, you know, both the single vertex. And it has the flow. It's 1 over 1. So the vertex ratio is 1. How about the degree ratio? So the degree ratio is I go out to n vertices and only 1 gets the flow, so the degree, our degree ratio is n over 1. So therefore the geometric mean is 1 times n, and then the square root of n. So that's the cost of the first stage. Now how about the second stage? So let me come back. So in the second stage, so what is the degree ratio? So here I have the vertex ratio, n vertices, and only 1 got the flow. So the vertex ratio also n, and that degree is a similar game, so it's also n, so the product is n squared, square root of n squared is n. So therefore I get a fantastic learning graph of complexity n, and you remember n is the trivial thing, n means that you have to ask all the n variables, so you don't have to work much to get n. So that's why it's a perfectly correct learning graph, except that completely trivial, not interesting. So how to make then an interesting learning graph for the... So here is the good learning graph. So here is the good learning graph for element. By good I mean that this is the learning graph which gives you the complexity, which is, you know, the truth n to the 2/3. And it's, you know, almost the same, except that, and now you remember what happened in the quantum world, except that I am kind of making, you know, one more stage. And this one more stage is at the beginning, I just gather a bunch of elements. And if you remember, that was the Johnson graph doing for the quantum world. So I am working on R element substance in the quantum world. So here, in this first stage, and this is why I'm always speaking about length, because it's kind of generalized stage, is that here I'm not going from singletons to, you know, from empty sets to singletons, but I am going from empty sets to all subsets of size, say, R minus 2. And therefore, you know, this is a kind of edge, whose length is really R minus 2. I could do this, you know, correctly. Okay, so this is the first stage. So without any thinking, I just gather all possible subsets of size R minus minus 2. And then the next stage is one more element, and the next stage is one more element. And this is really what I did previously. Okay, so here I am taking A, and here I am taking B, the two elements which collide. Except that now I have this bunch of sets before. Okay, so again, for the weights, it's just all possible R minus 2 element subsets. One more, that's the thing. Every weight is 1. And how about the flow? So here, at this level, I put a flow. So the flow, the flow goes uniformly out. And a vertex gets flow if it doesn't contain A and B. So A and B are you remember, the colliding elements. So if I gathered R minus 2 elements such that A and B are not there, then flow is there. If A or B is there, then there is no flow. Okay, that's detail. The more interesting thing is that then once you have here a flow, that is you are in a vertex which doesn't, a subset of size R minus 2 which doesn't contain A and B, then here there is one more element, and you send the flow if this element is A, and here you send the flow if this element is B. So that's the learning graph. I hope you see the strong symmetry with the Johnson work for the thing. And now, let's compute. Yeah. So it looks like, well, I will get nowhere in my talk, but maybe you will understand learning graph after this, which is something. So let's do it. It may be helpful. So how about the first stage? So let's compute as we did the vertex ratio. Yeah, it's always 1 in the beginning. It's fine. So how many altogether? How many vertices I have here? It's n choose R minus 2, and I don't want to include A and B to be getting the flow. So that's the number of vertices which get the flow, and this is basically the same. Yeah, so this is 1, and therefore you shouldn't forget, I don't want to cheat, that here I am loading R minus 2 elements, so therefore this is the length. That's the only place where the length comes in, and therefore this length is R, and times 1, this is just R. So the geometric mean is here, and then R times 1 is okay. So that's a stage which I am paying, kind of God knows why, but this R is, of course, I'm paying for it, but it will be helpful. So how about the second stage? So what is the, so you remember, okay, then second stage, obviously the vertex ratio here is, and here second stage, the vertex ratio is here is just the same as was the degree ratio there, and therefore the vertex ratio is just 1. How about the degree ratio? So if I am going back, then, so this, so any vertex will get one more element, so it can be anything but the R minus 2 which is there, so it's kind of n minus R minus 2, but the flow is going just into the vertex which loaded A. So therefore the vertex ratio is, the degree ratio is this small, so it's n over 1n, and you get the complexity. Now the length you can forget about, it is always 1, so it's just the geometric mean of square root of the geometric mean of 1 and n, so square root of n. So until now everything was simple. So now that's the interesting thing, the third stage. So how about the third stage? So how about the I am here. So what is the vertex ratio here? So how many globally how many black vertices I have? Notwithstanding the flow, it's just n choose R minus 1. Okay, so this is n choose R minus 1, and which one get the flow? So for the flow, A is already there, and then I have to choose, altogether I will have R minus 1 element, A is already fixed, so I have to choose R minus 2 out of the n minus 2, which is not A and not B, and now this is n over R. So that's interesting. So this vertex ratio became n over R, and the degree ratio is very similar as previously, so that's the same thing. It's again basically n, and therefore the complexity of this stage is square root of n over R times square root of n, which is n over square root of R. And now you sum up these three stages. The second stage is nothing, so if you optimize the first stage and the third is R plus n over square root of R, you get then to the 2/3. Okay, so it kind of works. Obviously, you don't really see why. So let me make one more slide, and then maybe you really understand that how learning graph do very simply, really basic combinatorics, not even combinatorics, sometimes interesting things. So how did we win? So how on earth this n to the 2 third came really up? So so you remember in the ith stage, length is there or not. The important thing is the square root of the vertex ratio times square root of the degree ratio. And so about the degree ratio, it's there. It's once for all. This is a local thing. But the vertex ratio is kind of interesting. It depends on the history. So obviously the vertex ratio, it depends what happened before. And if you think about a little bit how does really this vertex ratio evolve during this process, then so let's think about it. So for example, I am at the level the vertex is a minus 1, and then think about it that there are that many vertices at level a minus 1, and imagine that the out degree is 10. Then the next level, maybe I have 10 times as many vertices. If there is no collision, so every new vertex is separate, so for every vertex at the level a minus 1 creates 10 vertices, then I get 10 times more. That would be this much. But if you imagine that actually at this next level, every vertex gets 2 incoming edges, then I will get only 10 over 2, 5 times as much as previously. So really the new number of vertices at the ith level is the cardinality of the previous level times the out degree there, and the in degree at the previous level, and the in degree at this level. And again, I suppose total symmetry to be simple. Okay? And absolutely similar things for the flow. There is the flow, and then if F flow is always uniform, then you send out, but might be collisions. And this collision is diminishing the number of new vertices at the ith level. So if you just write it up, then what you get is that the new vertex ratio is the old vertex ratio times the ratio of the out degrees, the global out degree over the flow out degree, divided by the in degree in the new level, the global in degree over the flow in degree. So this quantity really will help you. This diminishes the complexity. So actually all I said here is something here. I am not sure that this helps you really, really much. Oh yeah, no, here it should. So okay, so again, how did we win? So the point is that we somehow, obviously, this stage we win. In the bad learning graph, this stage just was n squared, you remember. And now it became much less than n squared. It became this n over square root of r. Yeah? Well, I mean, if you're squaring it, n squared over r. So n squared over r instead of n squared, so I get this over r, and of course this r is 1, I am in the bad learning graph. So how did I get it? So, yeah. So really what happened is that when I was here, so I have to explain that in this stage I was winning, yeah? So that's what I am claiming with respect to the bad learning graph. So therefore I'm claiming that the vertex ratio here became much better than previously. So what is really the vertex ratio here? Well, just what I said, the vertex ratio here is the vertex ratio which was there times this out degree relation between the generic case and the flow and over the in degree. So let's see, this generically here it was, if you remember, 1. So basically I have as many vertices getting flow as not as altogether the vertices. So you can forget about this type of vertices. Think about it, everyone gets the flow. And then what is the out degree? So the out degree here, you remember, is basically n. I can add one more element and almost everyone is free. But the flow going just to one place, so this is n over 1, so that's working against me. But how about here? So here basically, again, the flow is a unique edge, so this will be 1. But on the other hand, if I have here almost r minus 1 elements, and here I have the subsets of size 1 less, then I have r possibilities to come. So if I have the set 1 to r, then any subset of these which doesn't contain ein is a potential father here, because maybe I added the ith element. So therefore here the in degree of the black in degree is r, and that's what diminishes my complexity. So that's why I'm getting the n over r, and that's how I'm getting. So basically, at the end of the day, it's kind of funny that this quantum gain is coming in a construction where you can, if I'm totally symmetric, construct a learning graph where somehow you get colliding flows. So that's my punchline. If the flow is colliding, that helps you. And this very simple things is, at the end of the day, translates to an improved quantum query complexity. Okay. So I guess I have to get into high level because clearly I am nowhere. So based on these principles, they are a few new quantum query algorithms. So I spoke about triangle. Now instead of triangle, you pick up your favorite fixed graph, the Petersen graph on 10 vertices, and then you ask that what is the complexity to find out if your input contains a copy of the Petersen graph. And so this is the subgraph parameterized by h. That's what you are looking for. When h is the triangle, then this is just the triangle problem. Then another problem which gets some results is associativity. Now I have an n times n table. Think about this as a multiplication for maybe a group, maybe not. And then the question is that is it associative? So can you find the triple ABC such that A times B times C is not the same as A times B times C? If there is such a triple, then it's not an associative operation. So again, trivially for this, the complexity is you can search over all triples. This is n cubed, grow over n to the 1.5. And then, so the new result is Alexander in his original paper improved triangle from, if you remember, 1.3 n to the 1.3 to n to the 1.296. And if I never believed that God made the world in a way that the complexity of the triangle is n to the 1.3, I even less believe that made the world in a way that it's 1 to the 2.96, and indeed it's not. But it was, improving. So that was his real application. He could show that the learning graphs give something better than quantum folk, at least potentially. And then this year so we improved the triangle to 9.7, which is what you see there. Of course, there are some points there. And we have generally an algorithm for any subgraph, which gives something better than the trivial. And for associativity, we can prove n to the 10 over 7. So this improves over the trivial Grover search, which is 1.5. Okay. Now, so I really don't want to do more than maybe now I have to say that, okay, so why did we do this? So was it necessary for the learning graph? So the learning graph, so basically the triangle is, we are doing something like in element distinctness. Here I am gathering a bunch of inputs. Here inputs are of course edges. So there is this database creation stage where I'm getting a lot of edges, and then I am putting there the triangle. And really not much more, except that there are a few little ideas. So it turns out that the triangle, a triangle means that you will have a big subset of vertices for A, big A1 here, a big subset of vertices for B, which is A2, and a big subset of vertices for the third A3 edge of the triangle. And then initially, you gather a bunch of edges between these subsets and then put A1 here, A2 there, A3 there, and create the triangle. That's it. I mean, for this, we could have done this with quantum works. You don't need learning graph. As it turns out, the optimal parameters are such that this huge subset A3 is just a singleton, and actually between these two really big subsets, the graph is the total graph, so the perfect, the full bipartite graph. Here, at least, it's not. So this A3 is not related initially to all the set, just some subset. So what I really want to say that this is, you just play unbinary, you play the obvious things. And there are two very simple ideas. So one simple is the sparsification, that you really don't have to load everything in the beginning. So here it turns out that this is the sparsification factor. And this was already in Yellow's paper. So that's how he got down from 1.3 to 1.29 something. And then the second, again, not that much revolutionary idea, that these sets don't have to be the same size. So here you see they are not at all. So that's in our paper. And once you have this idea, which is again a very simple algorithmic idea, and you put the necessary machinery, you got the result. And then you might wonder that why on earth had to wait for the learning graphs for this, and I really don't know. But it's definitely the case that somehow learning graph with the simplicity makes your thinking easier. So you are not lost in in some big Hilbert spaces between eigenvalues, which you might see but might not see an obvious thing. So here somehow it becomes again a very simple combinatorial thinking, and then you might have ideas which of course again you have to put down the quantum machinery, but at the end of the day give new results. So that's what I can say. And so about the associative, there is something which is maybe I should say before my time is over, is that one funny things about this learning graph is that if you followed what I was saying, the structure of the learning graph really never depends on the input. So really at every set, the S is just the index of the variable, but I don't care that what is the value of the variable. The weights are completely independent of the value what you learned. The only important thing is that I have to give the weights for an edge in the graph, which says that here I learned the first variables 1, 2, 3, and now I will learning the variable 4. But that what was the value of the variables first, second, third, I don't care. So this is a kind of very weird thing, so very not really fine, which also means that a learning graph which works for a problem automatically works also for another problem whose certificate structure is the same. So what do I mean? What I mean, for example, is that if you look at the threshold 2 function, that's a Boolean function, which is just the sum of the xi. So this is 1 if the sum of the xi is at least 2 and 0 otherwise. So what is a certificate here? Certificate is 2 bit, 2 indices I and j, such that xi is 1, xj is 1. And now I am claiming that any learning graph it computes, for example, the element distinctness automatically computes this one, and vice versa, which sometimes helpful, sometimes not. So, for example, for element distinctness, I already showed you, I just told you that this n to the 2/3 is the optimal quantum query complexity. So you cannot get better, which means that a learning graph will never be better for this function than n to the 2/3, whereas it's trivial to make a quantum algorithm which is square root of n. So the learning graph is extremely inefficient for this simple function. Well, there is some improvement. There are more sophisticated learning graphs which take into account also the values, and then we can have this more interesting learning graph which are optimal here, but you have to be aware of that. But this was a negative effect. On the other hand, it's also can be used algorithmically, that now if you created a learning graph for some function, then automatically you have a learning graph for any other function whose certificate structure is the same, and now you can think about more complicated functions. So what I am claiming really is that if we create a learning graph for 4 paths, and this is something similar, triangle, so you can do it, and I kind of explained that generically how we do it, but if you believe me that we can do this, and maybe I should say that in general, if you have a graph, then fixed graph, then you can, as the triangle, load subsets corresponding to the vertices of this, and then load edge sets corresponding to the edges of these things in any order, but they are only a fixed number of order, and once you fix the order, the optimal loading is a linear program. And Troy wrote a program for it you can find, which means that if you have in life any problem of this size, then you go there, let his program run, and it gives you the optimal learning graph for free, and you have a quantum algorithm. If it's not trivial, then you have a theorem. And if it's interesting. And so we did this for the 4 paths, and that's a generic case. And then my real point is that the certificates, so 4 paths, I mean 4 edges, so it's 5 vertices. This is 1, 2, 3, 4 edges. And all I'm saying that for associativity, the certificate has the same structure as 4 paths. So why? Because as I told you, for this I have to say that A times B, C is not the same as A times B times C. So here I put A, B, C. So the query is A times B, here B times C. Here I put the vertex B times C, and this is the query. Here I put the vertex A times B, this is the query. I just relabel these things, and then really you get A1, A2, A3, A4, A5, and of course it's directed, that has to be some relation, but at the end of the day, you can forget about direction. End of the day, you are interested that do you have in your say group table this type of 4 paths. And if you have it, then you are not associative. And therefore, the learning graph complexity of this much more complicated problem, which is associativity, the same as 4 paths. I don't claim that the query complexity is the same. But with the learning graph complexity is already interesting for 4 paths, then you get something non-trivial. Okay, I am totally out of time. I'm really sorry. Nested quantum walks, people again were inspired by the learning graph, and basically the very simple global idea which had to come up, and again it's kind of weird why we had to wait for the learning graph, that the data structure can be also quantum. And once your data structure is quantum, then you have it's almost trivial. Once you have this idea, you have to write down, but everything works out. You have a new type of work. So with this, basically, you get the quantization of this nested work. It's very nice. It's mostly the work of Stacy Frederick, and Robin Kotari. And so they could, but again afterwards. So once we had the algorithm for the associated triangle, then the nested work idea came out, and then of course it's very easy to make nested works which gives you the same thing, but it somehow had to wait for the learning graph. And then very recently, that's the last thing again, in 2 sentences. So what Alexander did is it defined a very, it's very nice. This I got 2 months ago. So basically he did a new type of quantization, and what he quantizes is basically well, it's again a reversible Markov chains, but he looks at them as electric networks, and the parameters he gets is usual parameters of this electric network, not the usual parameters of the quantum works. And I'm sorry, it's so basically what he can, the way he generalizes Szegedi's theorem is that okay, it's here, that he can have any initial distribution. So in the electric work sense, you can have any flow, any unit flow at the beginning. That's the initial distribution, and then he can quantize the wall corresponding to this electric network, which complexity is the geometric mean of the square root of the total weight, conductance in the language of the electric networks, 1 over resistances times the energy of this flow. Okay, and which is very nice is that this is true for any initial distribution, whereas for the Szegedi and all the other quantum heating type was always with respect to the stationary distribution. So you don't have to start in the stationary distribution. And once you have this, then it obviously creates a quantum work for any learning graph with the same parameters. So it means that you can create a learning graph, you have the query complexity, and immediately you have a quantum work which, the quantum normal complexity number of unitary gates and so on has the same complexity as the query complexity. And so this was used to give something about 3 distinctness, and again, so for 3 distinctness we are just as for triangle, God knows where we are having non-trivial results, but clearly not the end of the day. So these are a few concrete problems which are, so none of them is closed, and in some cases I guess the upper bound is correct, some cases the lower bound, some cases probably neither. I mentioned that the heating time in quantum still requires some thinking what is the good definition. Spoke about the second type of more adaptive learning graph, what is their power. Obviously there are other quantum works to be considered, just as Bialov's, and then finally this is kind of dreaming that there are some very nice classical works which do interesting things for the Lovász-Local lemma or for Schöning's algorithm of result. Is there any chance that we can say something non-trivial for the quantization of this classical algorithm? So non-trivial means more than Grover. Okay, I'm sorry again, at least today I started with it.
Any questions? So do you actually hope that you could get better than Grover for this for Schöning's algorithm? better than square root speed up, or like
Yeah.
any quantum walk speed up that's better than square
Not
root.
for churning, not for TSUP. I don't know. The Lorasto column, I don't know. I didn't think enough. But most probably not.
I have a kind of vague question. So an interesting thing about this dual adversary bound is there's no kind of temporal structure in the bound. You know, you just produce these vectors, and you don't have any kind of program or circuit. Whereas the learning graph model, you know, you have got this kind of temporal structure where you're kind of loading things. I mean, do you think there's some kind of deep reason why, if you want to actually find a good solution to this STP, you need to have some, you know, some kind of program that runs, you know, like temporally, or if it might be possible to find something directly, which just...
Well, I see more this flow way, the specificity of the learning graph, which helps. The timing helps. I don't know, that's an interesting idea. Maybe just an additional thing. Maybe it could be exploited.
What are the best lower bounds for this triangle?
Oh, the trivial thing. So,
And
absolutely trivial
still,
things.
yeah.
By the way, yeah, still, if anything, if you get something better for graph collision, maybe it's there also, yeah. So graph collision working both ways. So if you get better upper bounds for graph collision, you get better algorithm for triangle, better lower bound for the triangle. So this is again some extremely basic problem which we don't understand at all. Kind of, it's worse, you know, if you have in lack of open problems. Definitely, graph collision is one thing to look at.
If there are no other questions, then let's finish again.